On this video, we will complete our section 5.7 lesson. I still need to do for you a couple of cases of trig substitutions. So I'll do those, and then I will terminate this video and make a third video on which I do solutions to a random number of section 5.7 problems. So this this video is going to be section 5.7 lecture conclusion. Now, we were talking about trig subs during class last night, and in that lesson, we covered the first case. We said during class that trigonometric substitutions are utilized when we encounter these expressions in our integrand, a squared minus x squared. And there we said that we're going to use the substitution, or we're going to use the trig identity 1 minus sine squared theta equals cosine squared theta. Now, I lectured on that and gave an example of that during class, so I'm not going to do a lesson or do an example of that. What I am going to cover, though, is the second case, a squared plus x squared under the radical, where we're going to make use of 1 plus tangent squared theta equals secant squared theta. And then we're going to do the third case where you have a square root of x squared minus a squared. And there, of course, we're going to use our secant squared theta minus 1 equals tangent squared theta substitution. Okay. In all cases, a is greater than 0. So we'll pick up here with case 2. That would be this one. And the example I'm going to use here is the integral of dx divided by 4 plus x squared to the 3/2. Now, it's not always going to be the case that we're presented with this expression written exactly in this manner, where we have a radical and we have a squared plus x squared. Here, we're going to have to make note of the fact that because this is 3/2, this is really the integral of dx divided by the square root of 4 plus x squared cubed, right? Using our rules from algebra 1 of exponents. So we do have a square root of a squared plus x squared. So our job is to identify a. In this case, a squared is 4. So a is going to be 2. And we use the substitution in this case, x equals a tan of theta. Or in our problem, x is going to be 2 tangent theta. Now that means dx, right? Because we're going to do a trig substitution. We're going to replace this with whatever we calculate over here in terms of theta. Dx is going to be the derivative of this, which is going to be 2. The derivative of tangent, of course, is secant squared theta d theta. So when we rewrite our integral, right? When we rewrite our integral, we are going to want to replace 4 plus x squared to the 1/2 with this. Now, we can do that work in the problem itself, or we can do that work off to the side. Personally, I like to do that work off to the side and keep my integral area of my homework pretty neat. So I'm going to reevaluate, right, off to the side, what is 4 plus x squared? Well, 4 plus x squared is going to be 4, and I'm going to go ahead and do it with a radical. So that's going to be 4 plus x squared. X is 2 tangent theta, so that's going to be 4 tan squared theta when we square that. We're going to factor out a 4, and that's going to give us our before mentioned identity, when we factor out a 4, we have 1 plus tangent squared of theta. But we know that when we take the 4 out, that's going to leave us 2. And then we're going to have the square root by substitution of secant squared theta, and that's going to leave us 2 secant theta. So our denominator, 4 plus x squared to the 1/2, simplifies to 2 secant theta. Now, to finish this, we, of course, have 4 plus x squared to the 1/2 cubed. So we would want to cube this. So that's going to be, well, I don't think that's what we get when we cube 2. That's going to be 8 secant cubed theta. Okay. So that's what our expression is going to simplify to. Now, it's important that we note here, right, while we're working with this, that our assumption on theta is that theta is between negative pi over 2 and pi over 2. Theta is an element of the open interval from negative pi over 2 to pi over 2. This all goes back to our graph of our trig function. Our trig function has an asymptotic pi over 2 and an asymptotic negative pi over 2. And we're going to want to invert this. We're going to have to take the inverse of this tangent function when we complete this problem. And to make that function invertible, we have to limit the domain between negative pi over 2 and pi over 2. Open at negative pi over 2 and open at pi over 2 because those are vertical asymptotes. I know those are the kinds of things when we are in algebra 2 or pre-calc, we kind of ignored all these restrictions. Heck, some of us may have made it through calc 1 by ignoring all these restrictions. But that's not the world we live in anymore. These restrictions are now significant to us and a key component of a thorough and complete answer. So this is the explanation that we've got, and we're ready to do our substitution. We're going to come over here. We're going to rewrite our integral now. So now our integral is the integral. dx is written right here. dx is 2 secant squared theta d theta. So that's 2 secant squared theta d theta. Our 4 plus x squared cubed, 4 plus x squared to the 1/2 cubed, we've now calculated that by doing our trig sum. That is actually 8 secant cubed. Now, when we look at this integral simplifies, right? 2 goes in 8, that leaves me a 1/4 out front. I have secant squared divided by secant cubed. I end up with 1 over secant of theta d theta. Well, 1 over secant is cosine. This simplifies to 1/4 the integral of cosine theta d theta. So we took something that looked heinous in the beginning, dx divided by the quantity 4 plus x squared to the 3/2, and that integral, using the appropriate trig substitution, turns out to simplify to 1/4 cosine theta d theta. We know the integral of cosine is sine, so this equals 1/4 sine theta plus c. Now, as I explained last night during class, a key component of trig substitutions is we're going to substitute in place of x. In place of x, we're going to substitute theta. We're going to solve the integral using theta as our variable, but prior to completing the problem, prior to finishing the problem, we have to revert back to x. And the way we do that is we take our expression here, and this is where our inverse trig is going to come in. We rewrite this. I'm just going to copy it down here so I have more room to work. I divide by 2. X over 2 equals the tangent of theta, which means the inverse tangent of x divided by 2 is equal to theta. That allows me to put back in place of theta what I need theta to be. Theta is the inverse tangent of x over 2. Now, how am I going to do that when I have to find the sine of that? I'm not going to write sine of inverse tangent of x over 2. That's not going to be my answer. I'm going to then use this, draw a right triangle. I know tangent from back in the days of pre-calc. I know tangent is opposite over adjacent. I'll pick any acute angle, it doesn't matter. I'll call that one theta. So the opposite side is x, the adjacent side is 2. And if we utilize Pythagorean theorem, then the hypotenuse, of course, is the sum of the squares of the two adjacent sides. So we're going to get here that this side is equal to the square root of 4 plus x squared. How did we do that? We said, well, x squared plus 2 squared equals the hypotenuse squared, or x squared plus 4 equals the hypotenuse squared. And that led us to the hypotenuse is equal to the square root of 4 plus x squared. Just our friend, the Pythagorean theorem back from grade school. So what do we need to know? Well, to finish our problem, right, to complete our problem, we need to know the sine of theta. Well, the sine, right, from back in, again, algebra 2 pre-calc, sine is opposite over adjacent. So this answer then is re-expressed as 1/4. The sine of theta is opposite, which is x, divided by the square root of 4 plus x squared, right? Opposite over hypotenuse, plus c. And now we've completed our problem. We've put it back in terms of x. So we don't want to forget this final step. Now, this final step involves trig. We have to use the inverse of whatever it is we decided our trig sub was going to be. It's easiest if you just draw the triangle. It's always going to be a Pythagorean theorem problem. It's a right triangle. And you're going to have to remember, opposite over adjacent is sine, or opposite over adjacent is tangent. Opposite over hypotenuse is sine, or adjacent over hypotenuse is cosine. All right, so that's case 2. Now, for case 3, right, hold on, I'm going to just pause the recording here so I can erase this and save some time on the recording. I'll be right back with you. Okay, so for case 3, we have a clean whiteboard here. For case 3, we're going to be using looking for the expression x squared minus a squared in our integral. And so here for our example and our illustration, we'll do the following integral. We'll do the integral of the square root of x squared minus 16 over x to the 4th dx. Now, when we're doing trig sub problems, when we first write them down, they can be kind of intimidating. They're not necessarily things that we look at and think, oh yeah, I know how to integrate that. We have to trust the process, right? This x to the 4th is here for a reason. We're probably going to need it somewhere. They put it there. It's not there to cause us grief. It's there to assist us as we do the problem. So as we write these problems down, don't prejudge them just as you write them down and think, oh my gosh, oh my goodness, this problem is impossible. All the components of the integrand are there for a reason. And because they're there, they're going to assist us when we do the problem, not hinder us when we do the problem. So when we look at this problem, we identify this as x squared minus a squared. We know that that's not a squared minus x squared. Our constant is not the positive portion. It's not a squared plus x squared. We don't have a plus under our radical. Our constant is negative, so that comes under the third case, x squared minus a squared. We identify our a. A is going to be 4 here. And we know our substitution here is going to be x equals 4 secant of theta. Okay, that's going to be our substitution for the third case. First case, a sine theta. Second case, a tangent theta. Third case, a secant theta. Now we're going to find dx here. That's going to be 4. The derivative of secant, of course, is secant theta tangent of theta d theta. And now we have to do our substitution. Again, I like to work my substitution out off on the side. So I'm going to address x squared minus 16. Now my x is a secant theta. squared, that's going to present me, sorry, it's not a secant theta, it's 4 secant theta. So that's going to present me with 16 squared theta minus 16. Of course, I'm going to factor out the 16 and leave myself secant squared theta minus 1. Now, here, we're going to take out the 16, of course. That's going to leave us 4. Now, underneath, we're going to replace secant squared theta minus 1 with tangent squared theta. And that's going to give us 4 tangent of theta. Now, again, we have to note our restrictions on theta. Secant, right? Secant, we need this to be an invertible function. It needs to be 1-to-1, in other words. We remember how to graph secant, I hope. To graph secant, what we do, of course, is we graph cosine. Remember, this is pi over 2, and this is pi, and this is 3 pi over 2, and this is 2 pi. When we graph secant, we graph cosine, and then the graph of secant, of course, is found by starting here. Now, this is 0, so that's going to present us with an asymptote. When we take the reciprocal of this is also 0. That's going to present us with an asymptote. And then we graph secant by doing this, right? But this function itself is not 1-to-1. That doesn't pass the horizontal line test. We have to limit the domain. And the way we limit the domain is we don't use this portion here, because now my graph is 1-to-1. It passes the horizontal line test. And we choose not to use this portion here. So now my graph is 1-to-1. And now our limitations on secant are going to be 0, right? Theta is an element of the closed interval from 0 to the open interval of pi over 2, union the open interval, the closed interval at pi, right? Because we're defined here and here, and our asymptote is at 3 pi over 2. Now, some books may go between pi over 2, open at pi over 2 to closed at pi. It's just whatever your book tends to adapt. And to be honest with you, I didn't even look to see which one of those two things our book adapts. And I don't think they even talk about it, to be honest with you. I'm just perusing the book here for a second. They don't really even talk about it in our book, but we need one of those two limitations on our domain. All right, so we now know that our expression x squared minus 16 to the 1/2 is going to be replaced by 4 tangent theta. So we're going to come over here and we're going to rewrite our integral. X squared minus 16 to the 1/2 is going to be 4 tangent of theta. Now, what's going to happen on the bottom? Well, the bottom is x to the 4th, right? X to the 4th. X is 4 secant of theta. So we're going to have 4 to the 4th, right? 4 to the 4th is 256, I believe. We're going to have secant to the 4th theta. Now, don't forget, we still have to write down dx. dx is going to be 4 secant of theta tangent of theta, right? That's our full substitution. So when we take a look at this, we have a 4 and a 4 on the top. 4 times 4 is 16. 16 into 256 leaves us 16. So that's going to give us 1/16 the integral. Now this secant makes this secant cubed, right? So our denominator is going to be secant cubed theta. Our numerator is going to be tangent squared theta. And then there's our d theta, which I left off right here. So I apologize for that. Well, tangent squared over secant squared. That cries out to be simplified, right? So we'll come over here to the side and we'll think about this. Tangent is sine divided by cosine. So we have sine theta over cosine theta squared. That's my numerator. The bottom is secant cubed. That's 1 over cosine, right, theta cubed. Now, when I simplify that, I invert and multiply, right? Division of fractions. So I have sine squared theta over cosine squared theta times cosine cubed theta over 1. That simplifies, right? This turns out to be cosine to the first. That simplifies to, that's not how you spell sine. That simplifies to sine squared theta cosine theta. So this integral simplifies to 1/16 the integral of sine squared theta cosine theta d theta. That's a u sub, right? That's a u substitution problem. If we take a look at this problem and we say, I want u to equal sine theta, then du requires us to have a cosine theta d theta, right? The derivative of sine is we have a cosine theta d theta. This is du right here, and this is u squared. So we have to trust the process. We have to trust the fact that they put what they put in the problem, because it's going to lead us to something we can integrate. So ultimately, I'll write it in orange because it's going to be our u sub. We have 1/16. We have the integral of u squared. I already started to integrate. I apologize. Du. Now we know what that's going to be. That's going to be 1/3, right? So we have 1/16 times 1/3 u cubed plus c. But of course, that's not the variable we're working with. We've got to undo our u sub. So that gives us 1 over 48. U for us is sine, so that's sine cubed theta plus c. See, they gave us all the parts we needed, so the integrand presented itself. In the beginning is looking rather burdensome. Here it didn't look much better, but when we did the work and used our trigonometry, we turned into it turned into an integral that we can integrate just using a straight u substitution. We didn't need parts, we didn't need trig integrals, it was a straight u sub. But of course, we're not done. Problems in x, our answer's in theta. We have to still come off to the side and do our triangle work, right? We've got to do our triangle work. So what are we going to do? We're going to say x equals 4 secant theta, or x over 4 equals secant of theta, or inverse secant of x over 4, hence the reason we've limited the domain, equals theta. And now we draw our triangle. Again, pick any acute angle you want, all right? Doesn't matter, one of the two, as theta. Secant is hypotenuse over adjacent, right? Hypotenuse over adjacent, because it's cosine. It's the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. That means our hypotenuse is x, our adjacent side is a, and if we solve this, sorry, A4, not A in our problem, 4, if we do the Pythagorean theorem here, we're going to end up with this side being x squared minus 16. And I'm not going to waste your time with the Pythagorean theorem, but you can work it out when you do the problem. Now, this says I want the sine of theta. The sine of theta is opposite over hypotenuse. So our final answer to our problem, back in terms of x, our final answer to our problem is going to be 1 over 48. The sine of this is going to be opposite over hypotenuse. So that's going to be the square root of x squared minus 16 over x. We want to remember to cube that, plus c. All right, this is how our trig subs work. We take integrals, we believe that they gave us a problem we can solve, we identify which of these 3 approaches we're going to use, and then we just move carefully through the process. We set up our substitution for x. We find dx. We simplify whichever of these three expressions are there. We get an expression for that. It may take a little bit of time, but we get the expression for that. We put it into our integral. It grows and looks less nice, but it will simplify. We know it'll simplify because if it doesn't simplify, we can't do the problem. The problem's in the book, therefore it must simplify. Once we simplify it, we ask ourselves, how would I do this integral? Right? We now have choices on how to do integrals, right? We have just to remember, we have antiderivatives. Those are almost never the answer. Wow. We have u subs. We have parts. We have trig integrals. And then we have what we're currently working on, which is trig subs. Now, the good news is there's only one additional way to integrate in calculus. We haven't learned it yet. We'll learn it on Tuesday, but we only have one more technique to go: partial fractions. It is highly, highly important that you master all the ones I've written in brown before we get to Tuesday's lesson, right? Tuesday's the last one, but when we work with partial fractions, they're going to expect us to know all of these while we're solving partial fraction problems, because when we simplify our partial fraction problem, it's going to be expected that one or more of these techniques are necessary to solve what we're going to generate. So we want to master these. Now, again, additional video assistance is available online, not from me, but my recommendations are Patrick's, and I don't remember the letters that come after that. I think it's JMT, Just Math Tutoring. I think that's what that stands for. And I also like Professor Leonard. Those are two very good places to go for additional video help. There's thousands of additional videos out there on this, but you know, my students in the past have said those two websites they can associate with, or they can identify with, and they make sense to them. But if you have some other place you like to go, well, you know, by all means, use that as well. All right, that completes our lecture video on section 5.7. Now I'm going to make a separate video for the solutions to a random number of problems from section 5.7.